It's not exactly a secret that most people don't care for mathematics. They probably have bad memories of feeling stressed out in algebra class or of feeling lost in trigonometry. For many, the negative feelings start even earlier, in grade school. That's where they experience arithmetic. Lots and lots of arithmetic. Typically, the poor student is shown a lot of tedious, incomprehensible algorithms for manipulating numbers, and it's small wonder that so many come away thinking that mathematics just isn't for them. But permit me to demur. I think arithmetic can be fun, and in this lesson, I'm going to try to win you over to my way of thinking. I have no grand point to make with the items I want to show you today. I just want you to relax, think about some cool number puzzles, and come to understand why mathematicians regard numbers as just inherently beautiful. When I was a kid, my brother and I used to play a game called Crypto. The game was played with a special deck of cards. Each card had a number between 1 and 24 written on it. Each player was then dealt 5 cards. A single card was placed face up in the center of the table. This card was known as the objective. The players then raced to find a sequence of arithmetical operations that would turn their 5 numbers into the objective. You had to use all 5 of your cards. No fair just using 2 or 3 of them. That might sound strange, but an example will make the point clear. Suppose your 5 cards were 1, 2, 5, 7, and 10. The objective card is 11. Then the player might argue that 1 plus 2 is 3, then 3 plus 5 is 8, and then 8 minus 7 is 1, and finally 10 plus 1 is 11. That's not the only solution. Another possibility is to argue that 7 minus 5 is 2, then 2 minus 2 is 0, and then 0 plus 1 plus 10 is 11. I'm sure there are other solutions as well. Let's try a harder example. Suppose your 5 cards are 1, 2, 5, 6, and 17, and the objective card is 8. Now it's not so clear how to begin. You might notice quickly that 6 plus 2 is 8, but we still have to use the other 3 cards. If we can make 0 or 1 out of the other 3 cards, then we'd be in good shape. That's because 0 can be added to 8 to get 8, and 1 can be multiplied by 8 to get 8. But I don't see how to make either 0 or 1 out of 1, 5, and 17. Another strategy is to notice the 2, and then wonder if we can make a 4 out of 1, 5, 6, and 17. Unfortunately, there's no obvious way of making 4 out of those numbers. But there is a solution. Here's one way to do it. We argue that 2 plus 1 is 3, which times 5 is 15. Separately, we have that 17 plus 6 is 23, and now 23 minus 15 is 8. Pretty cool. Now here are 2 for you to try. The first, I think, is not so difficult. Suppose your 5 cards are 2, 5, 6, 10, 12, and your objective is 3. And here's a tougher one. Suppose your cards are 5, 7, 11, 19, 23, and your objective is 1. Why don't you have a go at those and see if I've made good on my promise to show that arithmetic can be fun? Any luck? How can we make 3 out of 2, 5, 6, 10, and 12? Well, here's one approach. We have that 12 minus 10 is 2. Then 2 plus 2 is 4. And then 4 plus 5 is 9. And finally, 9 minus 6 is 3. We could also have argued that 2 times 5 is 10. Then 10 divided by 10 is 1. Separately, we have that 12 divided by 6 is 2. And finally, 2 plus 1 is 3. I'm sure there are many other solutions as well. The second problem was to make 1 out of 5, 7, 11, 19, and 23. This one's harder, or at least I found it to be so when I tried to work it out myself. Here's one way to do it. We start with 23 plus 19, which is 42. And then 42 divided by 7 is 6. 6 plus 5 is 11. And then 11 divided by 11 is 1. As always, I'm sure there are many other solutions as well. I was fairly young when I played crypto with my brother. Later I learned, though, that this sort of thinking was at the heart of one of the most famous number puzzles of them all. I'm referring to the famous 4 fours puzzle. The game is to use exactly 4 fours to make as many other numbers as you possibly can. Now, when I say you have to use 4 fours to make other numbers, I mean you can use whatever mathematical operations you want. Certainly, you can use addition, subtraction, multiplication, and division, but you could also concatenate some of the 4s to make larger numbers. For example, you could take 2 of the 4s and then turn them into 44. You could also do square roots, or exponents, or anything else that occurs to you to use. To illustrate the idea, how would you make 0 with 4 fours? Well, one solution is to write this. 4 minus 4 plus 4 minus 4 is 0. That works. How about 1? Well, this time we could try 4 minus 4 plus 4 divided by 4, and that works out to be 1. But we could also do 44 divided by 44 is 1. There are many other solutions as well. How about 2? Well, again, here's one way. 4 divided by 4 plus 4 divided by 4 equals 2. I'll let you have some fun now. See if you can use 4 fours to make a few other numbers. 3, 4, 5, 6, as many numbers as you want. You'll find that you can get most of the numbers up to 100 with only very standard arithmetic. Pause the video here if you want to try this yourself. I'll just present solutions for 3 through 6. After that, you're on your own, or you can go to the internet to quickly find more solutions. Among the small numbers, 3 is actually one of the harder ones. Here's a solution that works. We do 4 plus 4 plus 4, which is 12, divided by 4 gives us 3. For 4 itself, we could go with 4 plus 4 times 4 minus 4, and that works out to be 4. And for 5, we have 4 times 4 is 16, plus 4 is 20, divided by 4 gives us 5. But just to show you how ingenious these solutions can get, let me remind you that 4 factorial, which is 4 times 3 times 2 times 1, is equal to 24. We usually write 4 with an exclamation point to denote the factorial. With that in mind, another way to make 5 is this. 44 minus 4 factorial divided by 4 gives us 5. In other words, 44 minus 24 is 20, which divided by 4 gives 5. And finally, here's a possibility for 6. We do 4 plus 4 is 8, then 8 divided by 4 is 2, and finally 2 plus 4 is 6. I think that's sufficient to make the point. The next time you find yourself waiting in a long line for something, have fun trying to find solutions for other numbers. As I got older and was exposed to fancier mathematics, I came to realize that there were surprising and almost unbelievable patterns to be found in numbers. For example, I learned about perfect squares, which you probably know are numbers that can be made by multiplying a number by itself. For example, we see that 1 times 1 is 1, 2 times 2 is 4, and 3 times 3 is 9, so 1, 4, and 9 are perfect squares. The next few perfect squares are 16, 25, 36, 49, 64, and 81, as you can quickly check for yourself. Nothing special so far. But then one of my high school teachers told me to check what happens when you start adding up consecutive odd numbers. We start with 1 equals 1, which is certainly simple enough. But then we have 1 plus 3 is 4, then 1 plus 3 plus 5 is 9, and 1 plus 3 plus 5 plus 7 is 16. It seems like we always get a perfect square. Let's see if this remains true for the next few numbers. 1 plus 3 plus 5 plus 7 plus 9 is 25, and 1 plus 3 plus 5 plus 7 plus 9 plus 11 is 36. We could keep going by noting that the next odd number is 13, and 36 plus 13 is 49. And then comes 49 plus 15 is 64, and then 64 plus 17 is 81. Isn't that cool? I sure thought it was when my teacher showed it to me. It's so surprising and completely unexpected. Odd numbers and perfect squares seem to be totally separate. And yet, apparently, they have this very deep connection. But the best is still to come. Once we find a pattern, we like to ask why the pattern holds. What is the connection between odd numbers and perfect squares? Does the pattern go on forever, or is it just a weird coincidence that works for small numbers? Let me show you a picture. Do you see what's happening? Starting from the single dot in the lower left corner, we have to add 3 to build up to the next square, which is 4. To get to 9, we add 1 dot to each of the 2 rows, then 1 dot to each of the 2 columns, and finally 1 dot in the corner. That's a total of 5 more dots. Building up to 16 means adding 3 dots twice, once for each row and column, and then 1 more for the diagonal. That's 7 dots in all. And then to get to the next square, which is 25, we add a total of 9 dots. Notice the sequence. We started with 1 dot, and then added 3 dots, 5 dots, 7 dots, and 9 dots to get the squares 1, 4, 9, 16, and 25. And once you understand what this picture is telling you, the pattern goes from bizarre and mysterious to totally understandable. This sort of thing just makes me smile. There's another reason I like this example. It establishes a connection between numbers and geometry. In math classes, we usually treat perfect squares as algebraic objects, by which I mean that we define them in terms of multiplying numbers by themselves. But they can just as easily be viewed as geometric objects. A perfect square is a number that can be arranged to form a square, as we saw in the figure. This suggests we should consider other shapes as well. How about triangular numbers? Maybe we should look at them. What sorts of numbers can we arrange into triangles? Let's look at some examples of what I have in mind. The first triangle has 3 dots, the second has 6, and the third 10. So let's say that 3, 6, and 10 are examples of triangular numbers. Looking at the pictures shows a clear pattern for where triangular numbers come from. We see that 1 plus 2 is 3, 1 plus 2 plus 3 is 6, and 1 plus 2 plus 3 plus 4 is 10, and so on. If we want numbers we can form into triangles, then what we want to do is to add up consecutive numbers. Since the first such sum is just 1 by itself, we'll treat 1 as a sort of honorary triangular number. We can now quickly check that the first 8 triangular numbers are 1, 3, 6, 10, and then 15, 21, 28, and 36. But now we might notice something else that seems bizarre and surprising. Watch what happens if we add up consecutive triangular numbers. 1 plus 3 is 4, 3 plus 6 is 9, 6 plus 10 is 16, 10 plus 15 is 25, and so on. We get the perfect squares again. Pretty neat. So now we have a genuine puzzle. Why do consecutive triangular numbers always add up to a perfect square? Pause the video if you want to try that for yourself. Think along the lines of our earlier diagram about summing consecutive odd numbers, and I'll bet you'll see what's going on. I think we can make a pretty convincing geometric argument for why consecutive triangular numbers always add up to a square. Here's what 1 plus 3 looks like. And here's 3 plus 6. And how about 6 plus 10 and 10 plus 15? Get the idea? We can always glue together 2 triangles to form a square. I think that visual arguments like this can be very convincing. An equation on a page can seem a bit lifeless, but a good picture can really make it come alive. On the other hand, let's not be too dismissive of the algebraic approach. When you're working with numbers, algebra and geometry work hand in hand. So let's go another round with our triangular numbers and perfect squares. We already have a very simple formula for producing perfect squares. We just multiply numbers by themselves. For example, we can say that the first perfect square is 1 times 1. The second perfect square is 2 times 2. The third perfect square is 3 times 3, and so on. In general, the nth perfect square is just given by n times n. No mystery there. The puzzle is this. Can you come up with a simple formula for producing the nth triangular number? Again, I recommend taking a geometric approach. Pause the video here to give it a try. The trick is to glue together a triangular number with itself. For example, here's what it might look like if we do it for 6 and 10. This time, we don't get a square, but we do get a rectangle. When we glue 6 to itself, we get a rectangle whose dimensions are 3 by 4. When we do it for 10, our rectangle has dimensions 4 by 5. Remember that the area of a rectangle is found by multiplying together the two dimensions. Now let's think about this carefully. 6 is the third triangular number, and when we add it to itself, we get 3 times 4. And 10 is the fourth triangular number, and when we add it to itself, we get 4 times 5. In general, we're going to get a rectangle with dimensions n by n plus 1. The area of a rectangle, remember, is found by multiplying together the two dimensions. Let's use t sub n to denote the nth triangular number. Then, if two copies of t sub n produce a rectangle, we can write down the equation 2 times t sub n equals n times n plus 1. And this implies that t sub n is equal to n times n plus 1, and all of that over 2. Let's try it out. Let me remind you that our first 8 triangular numbers were 1, 3, 6, 10, 15, 21, 28, and 36. According to our formula, the fourth triangular number is given by 4 times 4 plus 1 divided by 2, which is 4 times 5 over 2. That's 20 over 2, which is 10. And that matches our list. And the seventh triangular number is 7 times 7 plus 1 divided by 2. And that's 7 times 8 divided by 2, which is 56 divided by 2, and that really is 28. You might want to verify for yourself that our formula also gives the right answer for the other numbers on the list. So there's our formula. The nth triangular number is given by n times n plus 1, all of that over 2. Armed with this formula, let's revisit the question of why consecutive triangular numbers always add up to a square. If n times n plus 1 over 2 represents the nth triangular number, then the next triangular number after it will be found by replacing n by n plus 1 in the formula. The result is this. In other words, the next product of consecutive numbers after n times n plus 1 is n plus 1 times n plus 2. And that's why the top worked out like it did. Let's use this formula to see what happens when we add two consecutive triangular numbers. We get this equation. That might look like a big mess, but stay with me just a little longer. If you remember some basic algebra, then we can multiply out the top to get n squared plus n plus n squared plus 3n plus 2. And when we combine terms, this simplifies to 2n squared plus 4n plus 2. And when this is divided by 2, it simplifies down to n squared plus 2n plus 1. And once more, invoking our basic algebra skills, we have that n squared plus 2n plus 1 is n plus 1 squared. Do you see what happened? We've just shown algebraically that two consecutive triangular numbers always add up to a square. Algebra and geometry working together. I love it. Let's go off in a different direction now. When you first learn about numbers, you learn about whole numbers. You know the ones I mean, 0, 1, 2, 3, 4, 5, and so on. These numbers are very useful for lots of purposes. You can add them and multiply them all day long, though that probably would not make for a terribly interesting day. But at some point, you notice that things sometimes go wrong when you try to subtract. All is well for things like 5 minus 2 equals 3, or 12 minus 7 equals 5. No worries there. But if you try to subtract a larger number from a smaller number, things go badly wrong. What could 8 minus 9 possibly mean? If your whole world is just positive whole numbers, then 8 minus 9 is gibberish. It seems like it should be a number less than 0. But with positive whole numbers, there are no numbers less than 0. 0 just is the smallest number. You probably know where this is going. We want to include negatives in our collection of numbers. If we need numbers less than 0 to be able to subtract with impunity, then, by gum, we'll just make some numbers less than 0. We can say that 8 minus 9 is minus 1, for example. And once you think about it for a bit, negative numbers aren't really that eccentric. You can quickly come up with practical situations where numbers smaller than 0 actually mean something. 0 degrees Fahrenheit is a very cold temperature, but it's certainly not the coldest temperature there is. So negative numbers clearly have practical uses. But they also come with baggage. It's all well and good to make up numbers that are less than 0, but how do we do arithmetic with them? More specifically, what happens if we multiply one negative number by another negative number? I'll bet you remember the rule for this sort of thing. Somewhere along the line, some teacher told you that a minus times a minus is a plus. For me, it was Miss Oswald in the 6th grade. I remember asking her in class one day why that was the rule. It's certainly not the obvious choice for a rule. When I multiply a minus by a minus, my inclination would be to say that the answer is really minus. Miss Oswald made an analogy to spoken English, where a double negative is actually a positive. If you're not going to the movies, then that means you actually are going to the movies. Then she was off to the next topic. But I wasn't entirely satisfied with that answer. I thought, that's fine for going to the movies, but what does that have to do with multiplying negative numbers? So let's see if we can come up with a better reason for why a minus times a minus is a plus. In fact, I think we should make a puzzle out of it. Put me on pause and see if you can come up with an intuitive reason for why it's a good rule that a minus times a minus is a plus. Okay, let's see what we can do. We've already seen that sometimes taking a geometric approach can clarify facts about numbers. So let's try that here. Can we give a geometric interpretation to the question of multiplying negative numbers together? Perhaps we can. Consider a number line with an arrow pointing at the number 4. Now, I think it makes sense that if we multiply 4 by minus 1, then the result is minus 4. We could pause to give a precise algebraic justification of this, but I think this is natural enough that we can just take it as our starting point. So the effect of multiplying by minus 1 is to change the direction of the arrow without changing the length. But what happens if we multiply by minus 1 again? Well, we'd just change direction for a second time, and that would bring us right back to where we started. In other words, we interpret multiplying by minus 1 to mean that we're changing direction. And since there are only 2 directions on a number line, doing it twice brings us right back to where we started. I like that. This sort of thinking takes a seemingly arbitrary rule your teacher taught you and turns it into something that makes complete sense intuitively. But let's go one more round. We've now seen how geometry can shed light on the problem of multiplying negative numbers. But what if we take an algebraic approach to the same problem? Can algebra shed light on why a minus times a minus is a plus? I think it can. You see, it's all well and good to just make up negative numbers so that we can subtract without worry. The hard part is making sure that arithmetic with negative numbers satisfies all the same properties we know and love from normal arithmetic. Let me show you what I mean. To keep things concrete, we'll focus on showing that minus 1 times minus 1 is actually 1. And we can start with the observation that 1 plus minus 1 equals 0. That seems clear enough. If you add a number to its opposite, you get 0. Well and good. But in normal arithmetic, we also know that anything times 0 is still 0. And that leads us to minus 1 times 1 plus minus 1 is still 0. And now for the clever part. In normal arithmetic, we have something called the distributive property. If we apply that here, it tells us that we can distribute the minus 1 over the sum. The result is minus 1 times 1 plus minus 1 times minus 1 equals 0. And since we already know that minus 1 times 1 is just minus 1, our equation simplifies to minus 1 plus minus 1 times minus 1 equals 0. And finally, bringing the minus 1 to the other side gives us minus 1 times minus 1 equals 1. And there you go. That's why a minus times a minus is a plus. Now that we have negative numbers in our arsenal, we know that addition, subtraction, and multiplication are all working fine. But what about division? Even with the negative numbers, we're still going to have a problem with division. Sure, everything works fine if you're doing 10 divided by 2 or 14 divided by 7. But what if you want to divide 5 by 3? You know what's coming. We need to enlarge our repertoire of numbers again, this time to include fractions. We want to be able to say that 5 divided by 3 is simply 5/3. But to do that, we need to know how to manipulate fractions. Now, fractions are a near bottomless pit of interesting questions and puzzles. For example, why is it that when we add fractions, we have to find a common denominator, but when we multiply fractions, we go across the top and across the bottom? But we're almost out of time. So let me just show you one fun puzzle related to fractions. This one has a story attached to it. One day, an elementary school teacher was giving a test about reducing fractions. There was one student who she knew was struggling with the class, so she wanted to include fractions where the student would get the right answer, even though he didn't really understand what he was doing. So the first fraction she gave was 16 over 64. Of course, this simplifies to 1/4 because 64 is actually 16 times 4. But the student took a more simple-minded approach to reducing fractions and just crossed out the 6's. Interestingly, for this fraction, that actually leads to the correct answer. The next fraction was 49 over 98. The student just crossed out the 9's to get 4 over 8, which is again correct. This further reduces to 1/2, of course. The puzzle is this. Can you come up with 2 more fractions that are like this? Pause the video here if you want to think about it. Any luck? Well, how about 26 over 65? If you cross out the 6's, we're left with 2/5, which is correct. Notice that 26 and 65 are both multiples of 13. The last one is 19 over 95. Cross out the 9's to get 1/5, which is again correct. Very nice. But I don't recommend reducing any other fractions this way because these are the only ones for which this works. At least, these are the only ones where the top and bottom are both 2 digits where it works. Oh, by the way, did you hear what I just said? I talked about the top and bottom of a fraction. Mathematicians say top and bottom. When you talk about the top and bottom of a fraction, everyone understands what you mean. Instead, we teach little kids to say numerator and denominator, and then we wonder why they don't like math. Okay, one last quick puzzle before we pack it up for the day. There's only one number that has its letters in alphabetical order when written in standard English. Can you think of what it is? The answer is 40. See, numbers are fun. See you next time.